Hi, good afternoon, everyone. So, welcome to week 7 lecture. So, this is our lecture 6. As you may know, so we are approaching the end of chapter 2 and chapter 3 together. So, we were teaching the arch model, which on your lecture note, which on your lecture notes is the end of chapter 2. So we have taught some of the chapter 3, haven't we? So these are estimation of the ACVS and the ACF, the autocovariance function, autocorrelation function. And also you will estimate some asymptotic results. So all of these we have we have done, but remember, so as usual, so you please go back and revise on the lecture notes. So there could be something that I haven't talked about in the lecture note. So a highlight of something like that will be in exercise 5. So if you haven't done that, so in one of the ARMA models, that ARMA model can actually be reduced. So what do I even mean by a reduced ARMA model? Okay, so what I mean is the ARMA model can actually be simplified to a simpler model. And in the lecture note, I actually talk about something like that, which I haven't talked about in the lecture because I don't have time, okay? So have a read of the lecture notes, okay? So that's what you need, really. And I hope I today can finish all of chapter 3, so the prediction equation, forecasting of time series, and so on, as well as the generalized arch model, the Arch PQ model, which I'm going to talk about in the first half of the lecture today. Okay, so if, as usual, if any question, please let me know. Okay, please stop me, raise your hand, etc. Otherwise, so let's go back to the last part of the last lecture, which is the arch model. I was talking about an arch model, which is not enough for us. So this is the lecture note, so let's look at the lecture note this time. Let's not waste this beautifully created graph here. So this is the S&P 500. So last time I used some other stocks to demonstrate, but it's the same. So S&P 500, so you can see very persistent volatility clustering. So volatility clustering is one major highlight of arch model, which we hope the model can replicate these kind of so-called stylized facts of this financial time series. So volatility clustering is actually explained through a lag of the xt minus j squared in the arch model, but it's actually far from enough. So if you look at real data again, so if this is daily data, and the clustering is actually sometimes over a year, okay? So a year and a half in 2008, and in 2020, so more than half a year. So after a very volatile period, after the financial crisis, 2008, and the COVID-19 period. So this kind of persistence, if you want to replicate an arch P model, fine, your P has to be in the order of hundreds, which is completely non-practical, okay? So no people will talk about an ARMA model of order more than 10, okay? So let alone the hundreds. This is basically like an AR model with 100 parameters. So no one talk about that. So what do we miss? Well, we miss something that is actually similar to an AR model improved to an ARMA model, okay? So let's have a look at what we're going to talk about. Oh, sorry. Okay. So today we're going to start off with the Arch model, which is the generalized gauge. In the shorthand, usually people will just write it as gauge PQ. So what is gauge PQ? And the purpose, as I said, so in arch model, persistence in volatility is far from enough. Relative to what we see in real data. Relative to real data. So what do we suggest? So we improve it to a gauge model. Your model is the same for xt. So xt is basically I d epsilon t multiplied with a certain sigma t, which is the volatility equation, an explicit volatility equation. But now our sigma t square will be different from the arch p. Well, we should say similar, so it also has p terms here, which is xt minus 1 up to xt minus p squared, but we also add the path values of sigma t squared themselves. And A naught, AP, BQ are all strictly larger than 0. All other parameters are at least non-negative. So they're at least non-negative. Otherwise, that could make sigma t squared potentially negative, which is not what we want. So we restrict them to be at least non-negative. And A naught has to be larger than 0, otherwise it's actually non-stationary in the end. So I'm not going to talk about a non-stationary kind of gauge model. And AP, sorry, that's AP. And BQ are actually positive constants because they need to define the order of the gauge model. Okay, so this is P and Q, order P and order Q. Okay, so what's the property of this gauge model? So is it going to be more persistent in its volatility? So let's consider this gauge 1,1. And by the way, gauge 1,1 is still an industry standard. It means people will usually compare to gauge 1,1 for whatever you propose is performance relatively good compared to gauge model, or it's actually superior to gauge 1,1. If it's actually similar to gauge 1,1, then there's no point in proposing something else. Gauge 1,1, look at that. How many parameters are there? Only 3 parameters. Okay, so to potentially model this kind of complicated volatility behavior, which is actually fantastic. So this is the volatility equation. So sigma t square is dependent on xt minus 1 and sigma t minus 1. Now we can actually write sigma t square collected on the left hand side. So I hope you remember this backward shift notation, so it's not behind us at all. So arch and gauge model has closed relationship with our model actually, so we'll see in a minute. So if we collect sigma t squared on the left hand side, so it's 1 minus b1, b is the backward shift operator. Now if you have, remember how to invert this kind of operator, in particular here, if b1 is less than 1, well b1 is positive, at least not negative, so no need to write absolute value of b1 is less than 1, it's just b1 less than 1. Then 1 minus b1 times b inverse exists, right? This is something you learn when you learn about stationarity and how to convert AR to MA infinity. So in the end, if we can do this, then sigma t squared can actually be written as 1 minus b1 b inverse on a0 plus a1 xt minus 1 squared, which is what? I do it quicker this time, so you verify this. Sorry. So b1 to the power j xt minus j minus 1 squared. Okay. So it's basically 1 minus b1 b inverse applied on a0, that will be a0 divided by 1 minus b1. And if applied on xt minus 1 squared, then it basically becomes sum of b1 to the power j, xt minus 1 squared, well, taking j step behind, that is xt minus j minus 1 squared. Okay. So why do I do this? Why do I make sigma t squared dependent on past xt's? Well, at this point, you should see the difference between gauge and arch model, where arch model is actually dependent on finite number of past xt squareds. Here, even gauge 1-1 model depend on potentially infinite number of past observations. You want persistence, right, in volatility. Well, how about dependent on infinitely many past observations? That should provide more persistence to your volatility. Okay, and that's why people make sigma t squared explicitly depend on past sigma t squared. Okay, because when invertible, like what we have shown in this gauge 1-1 example, then certainly sigma t squared will depend on all many past xt squares, which make persistence more achievable reality for your model. Okay, so what else? What other properties of the arch model? So there. So let's do that. Sorry. So in arch P model, we talk about showing that it's a white noise, is that? So let's do that. So let's find the expectation of xt first, which is completely the same. Because sigma t is also dependent on information up to t minus 1 only. So it will be completely independent of epsilon t, which is IID noise, okay? And so of course then this will be 0. And for a lag variable which is positive, what is covariance of xt plus h and xt? Well, it's basically the same, okay? So it's, we expand the one that is xt plus h because it has a larger time variable. So it's the expectation of the product. The mean is 0. And epsilon t plus h is actually independent of sigma t plus h times xt. So the calculation is completely the same as when we deal with arch model. Okay. So this is 0. xt times sigma t plus h. So it just belongs to information up to t plus h minus 1. And of course then this is independent of epsilon t plus h. Okay. So you can write this formal notation. Now if we want to show that is white noise, then we need variance of xt. Well, variance of xt depend on the information given to you. It's basically the same, so let me give you a very quick example. If we go back to an arch 1, then expectation of xt square, remember, is expectation of sigma t square multiplied with expectation of epsilon t square, which is expectation of sigma t square. And if you expand this, expectation of sigma t square is a0 plus b1 expectation of xt minus 1 square. So if you iterate it, say m times, what do you get? You get b1 to the m, and then expectation of xt minus m squared, right? And then plus, so a naught is always there, is b1 part j from 0 to m minus 1, right? Just basically you iterated m minus 1 times, so verify this yourself, okay? Verify this yourself. Okay, so what do I want to do here? So I just want to show you here, if we are given b1 is less than 1, then what do we have here? Then it implies that as m goes to infinity, your expectation of xt squared is going to, well, the first term goes to 0, of course. Second term, so it's basically a geometric series, so that's a naught over 1 minus b1. Okay, so the information given is actually b1 less than 1. Then you can use the arch 1 equation to show that, okay, expectation of xt squared, of course, has to be going to be finite and time independent, okay? Because it starts from minus infinity. I haven't talked about initial starting point. That means it goes back to minus infinity. So you can confidently take m goes to infinity, okay? So then you prove that variance. So variance of xt here is actually finite and time independent. All right. So if you're given other kind of models, so this is arch 1, so if you're given other models Then it depends on what information given to you. So you want to ultimately show white noise, then it depends on what information given to you. Okay. Let's go back to a gauge, general gauge PQ. If your XT actually follows a gauge PQ, then this is important. Then your XT squared actually follows an armor model with order max of PQ and Q. If your fourth order moment is finite and time independent. So we always talk about in financial time series, your XT looks like a white noise, which we kind of proved, and XT square is not a white noise. Well, of course XT square is not a white noise. XT square look more like an armor model. And here is something that show you that gauge model is really a good model for this volatility estimator. So if we are going to provide a proof, then the proof will consist of, first of all, letting this eta t is xt square minus sigma t square. Then your xt square will be sigma t square, take sigma t square plus eta t, right? It's just rewriting the model basically. But what is sigma t square? Your sigma t square is a0 plus a1 xt minus 1 squared plus up to ap xt minus p squared, and then plus b1 sigma t minus 1 squared plus all the way up to bq sigma t minus q squared, and then plus eta t. So if we want to show really xt square is an armor model, then we need to remove sigma t squared, okay? So you cannot simplify the xt squared, but you actually can simplify this part here, because sigma t minus j square is xt minus j square minus eta t minus j. So sigma t minus 1 is what? Xt minus 1 square minus eta t minus 1. That's from our definition here. All the way up to bq times xt minus q squared minus eta t minus q, and then plus eta t, of course. So now we can collect the terms. So t minus 1 squared, so that's a1 plus b1. And all the way up to now, there is AP xt minus p squared and BQ xt minus q squared. So how to collect them? Well, if we write this as notation, if you take max of PQ as the order, for instance, if P is larger than Q, let's suppose P is larger than Q. Then you have xt minus P square and AP here, which is actually of order larger than Q. So BQ xt minus Q square. So we will assume, we'll extend BQ plus 1 up to BP. But all of them equals to 0, okay? If P is larger than Q. And vice versa, if Q is larger than P, then we'll extend AP plus 1, AP plus 2, all the way up to AQ. Well, they are all 0, okay? If we do this, then this order and this order can actually be aligned. So the maximum order is A max of P cube plus B max of P cube, and xt minus max of P cube squared, okay? And what you're left with is order eta, so plus eta t. The only thing difference is that here is minus b1 eta t minus 1 minus beta 2 eta t minus 2 minus up to bq eta t minus q. Well, does it look like an armor model? Well, it does look like an armor model, right? And the first order is max of PQ. The second order is, well, up to T minus Q, so this Q. But wait, of course, if we only can prove that eta T is a white noise. That's the definition for armor model, okay? So this noise time series has to be a white noise. Well, is it a white noise? Let's verify that. So that's the equation, okay? So let's verify if it's a white noise. First of all, the expectation of eta t is xt squared minus sigma t squared. So this time you don't need to expand anything on sigma t squared. You expand the xt squared to make it a product. So it's sigma t squared multiplied with epsilon t squared minus 1. Basically just expand xt as sigma t times epsilon t. So which is expectation of sigma t squared multiplied with expectation of epsilon t squared minus 1. Of course, this is 0. Sigma t is independent of epsilon t. So any function are independent, so in particular epsilon t squared minus 1 is independent of sigma t squared. How about covariance? So let's say for h larger than 0, covariance of eta t plus h and eta t. Well, we use kind of the same trick. So it's expectation of eta t and eta t plus h. So we only expand eta t plus h this time. What do we get? That will be sigma t plus h squared times epsilon t plus h squared minus 1 multiplied with eta t. But then the same trick applies. So sigma t plus h squared times eta t is actually independent of epsilon t plus h. Because this variable, again, is only up to information t plus h minus 1. So this is 0 again. Expectation of epsilon t plus h squared minus 1 is 0. So we're almost there, right? Eta t has mean 0, eta t has 0 correlation, 0 autocorrelation, Now, how about is variance? Actually, the variance is the most difficult part, okay? So the variance is eta t squared expectation. And naturally, it will be up to the fourth order moment of sigma t. So everything is squared. What is epsilon t squared minus 1 all squared? This is at least independent of sigma t to the power 4. So that write it as an independent expectation, squared it, which is epsilon t to the power 4 minus 2 epsilon t squared plus 1. What is the value of this? Well, that's one thing you need to know for Gaussian distribution, right? Epsilon t is standard Gaussian. Standard Gaussian has 4 order moment equals to 3, right? So it's 3 minus 2 plus 1, that's 2. So this is something you need to know, okay? So what then? But your expectation of xt to the power 4 is expectation of sigma t to the power 4 times expectation of epsilon t to the power 4, which is 3, times expectation of sigma t to the power 4. Which means that expectation of sigma t to the power 4 is actually 1/3 of expectation of xt to the power 4. And therefore, your eta t to the power 4 is 2/3 of expectation of xt to the power 4. So, usually, you need to deduce if your fourth order moment of your time series is actually finite and independent. And this, usually in this kind of question, is given to you. So if given, your fourth order moment is finite and time independent, which indeed is given to you from the beginning. Written expectation of xt to the power 4 is finite and time independent, okay? So that's explicit here. Then so does the fourth order moment for eta t squared, eta t. And so you approve, so eta t is a white noise. Eta t squared, not fourth order moment, sorry. So eta t is a white noise. And that's the end of the proof, right? So we just need to prove eta t is a white noise after showing that your xt squared indeed obtain this kind of armor model representation with eta t potentially is the white noise time series. And we just proved that it is indeed a white noise, okay? So you need to know how to prove this, okay? So if I give you an AR1 model, if you an Arch1 model, can you prove that xt squared is actually an AR1 model, right? Etc. etc. So you also, at the same time, can see that, okay, gauge model is really useful and it aligns a lot with real data. So real data tells you that xt squared, it doesn't look like a white noise at all. In fact, it looks more like an, if you look at the ACVS again, it looks more like an armor model. So there you go, gauge PQ implies xt squared indeed is an armor model. Okay? So a little bit more calculation, okay? So bear with me. So let me do this quickly. So if you can assume XT follows a Gauge 1-1 model, and is stationary, and what do we have? So we have your XT is sigma t epsilon t, and your sigma t square is this Gauge 1-1 equation. So let me do this a little bit quicker to show you a little bit more, okay? And therefore, your expectation of xt square is just expectation of sigma t square. So this is, hopefully this becomes standard calculation now. So expectation of sigma t square, well, equals to A0 plus A1 expectation of xt minus 1 square plus B1 expectation of sigma t minus 1 square. And if it's stationary, that means what? That means all of these are expectation of xt square, right? But this is expectation of sigma t minus 1 square. Well, we have proved that expectation of xt square is expectation of sigma t square. So expectation of sigma t minus 1 square is expectation of xt minus 1 squared, which in turn is expectation of xt squared. So therefore, expectation of xt squared is A0 divided by 1 minus A1 minus B1. So necessarily, of course, you need A1 plus B1 is less than 1. And we talk about kurtosis of this process, okay? So what is kurtosis of xt? It's defined as the fourth order moment, fourth order centered moment, center is at 0, so it's xt to the power 4 divided by the square of its variance. So fourth order moment divided by square of variance is always the definition of kurtosis. And I'm going to spend a little bit of time to show you that this is larger than 3, okay? And it implies that your xt cannot be a Gaussian process. So we talk about Gaussian process, right? Your Armour model, MAAR. If your epsilon t is a Gaussian, then your Armour model automatically is a Gaussian process. Here is different. So for arch and gauge model, even your epsilon t is IID normal, so Gaussian process. Ultimately, the xt itself cannot be a Gaussian process because the kurtosis can always be proved to be larger than 3. So let me show you how to do this, okay? Very quickly. And you repeat this in exercises, okay? So this is important to know. So your expectation of, first of all, your expectation of xt squared is A0 divided by 1 minus A1 minus B1, right? That's what we have just calculated. Now how about expectation of xt to the power 4, which is 3 times expectation of sigma t to the power 4, which is 3 times A naught plus A1 xt minus 1 squared plus B1 sigma t minus 1 squared all squared. So that's expectation of this all squared. So yeah, quite complicated, okay? So I'll lead you through this. So expectation of, so there's a big bracket here. So let's do this quickly. A naught squared plus A1 squared xt minus 1 to the power 4 plus B1 squared sigma t minus 1 to the power 4 plus all the cross terms, right? 2a naught a1 xt minus 1 squared plus 2a naught b1 sigma t minus 1 squared, and then finally plus 2a1 b1 xt minus 1 squared sigma t minus 1 squared, okay? So there's no other way to avoid this tedious expansion. Well, fortunately, so if it's stationary and if you assume that fourth order moment is time independent and finite, then you can simplify this, right? So this is, we still write 3 outside, and then take expectation on all of these things. So a1 square, that's expectation of xt to the power 4, whenever we can write this. So plus b1 square, expectation of sigma t to the power 4. Okay, and sigma t to the power 4 is 1/3. Xt to the power 4. And then plus 2a naught a1, well this is 2a naught square a1 divided by 1 minus a1 minus b1, right? And then the same here, expectation of sigma t minus 1 square is expectation of xt square. So is the same, 2a naught square b1 divided by 1 minus a1 minus b1. And then finally, so hopefully I haven't made any mistakes, okay? So 2a1 b1 times expectation of, we need to expand this. Expectation of t minus xt minus 1 square is sigma t minus 1 square epsilon t minus 1 square. So it's 2a1 b1 divided by 3 expectation of xt to the power 4, okay? So if you can't follow, verify this please, when you have time. So you basically expand xt minus 1 square to sigma t minus 1 square epsilon t minus 1 square. Epsilon t minus 1 square is independent of sigma t minus 1 to the power 4, okay? So when taken expectation, it's just expectation of sigma t minus 1 to the power 4. And the expectation of sigma t minus 1 to the power 4 is 1/3 of expectation of xt to the power 4. So, left hand side is expectation of xt to the power 4, right hand side or expectation of xt to the power 4. Good. So, let's multiply the 3 inside first. And then plus 6 a naught squared, a1 plus b1 divided by 1 minus a1 minus b1, right? Yeah, I think so. So therefore, your expectation of xt to the power 4, so finally, you can simplify this. Oh. So if you take this on the right hand side, so 3a naught squared minus 3 a naught squared times this plus this. So it's 3a naught squared times minus 3 plus 6, so it's plus 3 a naught squared a1 plus b1 divided by 1 minus a1 minus b1 yeah, and then divided by, we're taking out all these, okay, so it's 1 minus 2a1 b1 minus b1 squared minus 3a1 squared. So I hope I haven't made any mistakes. So if you divide it by x to the power 4 divided by the square of the variances. That's the kurtosis, right? So kurtosis will be 3 times 1 plus a1 plus b1 times 1 minus a1 minus b1 and then divided by this 1 minus 3a1 squared minus 2a1 b1 minus b1 squared. Okay? So yeah, I don't think I've made a mistake. So, well, we calculated kurtosis, so what? Well, remember what we want to show ultimately. I said it cannot be a Gaussian process, right? Why can we see that it cannot be a Gaussian process just from this? Well, we can see that it has to be larger than 3. So there's a very convenient 3 coming out. So is this ratio here involving a1 and b1 larger than 1? Well, this equals to 3 times 1 minus a1 plus b, 1 minus a1 plus b1 all squared. And then divided by 1 minus a1 plus b1 all squared minus 2a1 squared. Yeah? So 1 plus a1 plus b1 times 1 minus a1 minus b1. So that's 1 minus a1 plus b1 squared. And then the denominator can be simplified like this. Okay, so why do I want to simplify this? Because this way now I can see definitely it's larger than 3. Numerator is 1 minus a1 plus b1 squared. Denominator is the same thing minus something. Denominator now has to be smaller than the numerator. So this ratio has to be larger than 3. There's no way around it.
Can the
Yes.
sign flip? Like, can the denominator be negative or something? Or that one?
Sorry?
Can the denominator be negative?
It cannot be. A1 has to be positive. So all the parameters here at least are non-negative, okay? And in an Arch 1-1 model, A1 of course is strictly positive. So therefore, it's larger than 3. So therefore, it cannot be a Gaussian process. And that's what we want. We don't want these financial returns somehow go back to Gaussian process. It means it's again very restrictive. Okay, so Gauge 1-1 model is not a Gaussian process, so that's good. So let's look at some real data example. So before I give you a break, okay? So let's see. So you need to practice these exercises anyway, okay? So I just give you something to remember to do in the lecture. So
the Gauge 1-1 doesn't assume that financial returns are normally distributed.
No, the financial return are not normally distributed.
No, I know they're not, but
Yeah.
it doesn't assume so.
It doesn't. Yeah. So the gauge model itself is only the epsilon t's ID normal. In fact, most people may deviate from Gaussian. They think the epsilon t can just be independent, just IID observations, not necessarily Gaussian. Okay. In fact, if you remember, I talked about the leverage. This is not financial statistics, okay, but I talked about leverage at the start of this topic. Epsilon t is a symmetric distribution if you assume it's normal. Leverage means it's asymmetric. Yeah. So there's something called E-gauge. They exactly assume epsilon t is non-asymmetric. Okay, so perhaps you have seen that. Okay. So yeah. But yeah, I'm not going to talk about that. Okay, and I'm not spending too much time on that. So this is as far as we go. So Gauge 1-1 model is not a Gaussian process. Even your epsilon t is normal. Now, if you look at the, I want to show you this. This is, first of all, if you go to all our scripts in Moodle, so there's a gauge analysis you can download. So open our studio, so our studio can read this our script. So so play around this. What is AAU? A FIFA, I think. I don't know. So there has to be some FTSE 100 stocks. So yeah, let's assume it's a FIFA or whatever stock. So whatever stock that is, so it will be good to demonstrate it. So let's use QuantMod to download this stock price data, and then plot the return. AU is, so it's not available now? Okay. No, I think. Huh. See if I can. Yeah, sometimes some stocks suddenly you cannot get data from. So last time I checked, I can get data for AAU, but not this time. So yeah, let's change that to the Microsoft. Okay, yeah, Microsoft, fine. So then it's MSFT. That should be the 6th column. The adjusted price. So we've done this before, the Microsoft return. Okay, so far so good, so up to yesterday from 2007. And what I want to show you is this. So if we fit a Gauge 1-1 model, So this is, by the way, how to fit a gauge 11 model, okay? So why gauge 11? So you can change the order in this gauge, function. But usually people will not change the order, so gauge 11 is the industry standard, as I said. So the output, I will not test your output, by the way, apart from the seasonal ARIMA, okay? So seasonal ARIMA, you need to be able to write down the AR, MA, seasonal AR, seasonal MA. But other than that, I won't test you this kind of output, okay? Yeah, and ask you questions about that. But here, you can see that the A0, A1, and B1, okay? So it gives you these coefficients. Now, I want to calculate A1 plus B1. Why am I interested in A1 plus B1? If you remember those formula before, variance of xt is A0 divided by 1 minus A1 minus B1. Everything depends on A1 plus B1 is actually less than 1. Or at least not too close to 1. And look at it here. Is it close to 1 enough? Well, it's not too close. But if you restrict it to, let's not do that, okay? Try it yourself. If you restrict your time period to say just around 2008 or around the COVID period, 2020, you will see that A1 plus B1 is 0.99 something. Okay? So interesting, because we don't want this to be too close to 1, and yet they are quite close to 1, especially in very volatile period. Okay? So this A1 plus B1 in gauge 11 model basically is to control the magnitude of variance and kurtosis. And in those very volatile periods, perhaps it's better to assume that it's not actually finite, because they suddenly shoot up. Okay, so the magnitude is really huge. Okay, and it's reflected in the magnitude of the gauge 11 fit for A1 plus B1 actually. Okay, so try this. For those volatile periods, try fit a gauge 11 model and see what A1 plus B1 is. It will be 0.99, 0.8 something, 0.998, 0.99 something. Which indicates to you, yeah, it's approaching its limit. Okay. Stationary gauge model assume that these kurtosis, variance, they are finite, but it's approaching infinite basically relative to other model scale. So that's the story that you should take. And what else? I think, okay, it's over time anyway. So I'll give you a 5 minutes break, okay? So please come back at 2:09, and then we'll continue with another topic, okay? Okay. So let's get back to. Well, there's some. Yeah, I have to. So let's get back to what we were talking about. So we were talking about the sum of the fitted coefficients close to 1. So that's one thing. The other thing is I want to show you is the fitted model for this gauge 11. So I'm using this Microsoft data. So that's the return data, and that's the fitted volatility data. Okay. So the fitted volatility makes sense. So in more volatile period, the fitted volatility is larger. So this in around March of 2020. So the volatility shoot through the roof. Okay. So it's suddenly this huge spike in the magnitude of the return. Okay. Negative, more negative than positive. Okay. And it shoot through the roof. Okay. So it makes sense. But again, as I said, the A1 plus B1 in this gauge 11 model is quite close to 1 because of these two periods. Okay, so 2008, the financial crisis back in then, and then there's the COVID, start of COVID, 2020. Okay, so without these two periods, you'll find that the A1 plus B1 is quite much smaller than 1. But if you feed your data around these periods, then you'll find that A1 plus B1 is even larger, very, very close to 1. Okay. So yeah, one last thing about arch and gauge model before I move to another topic. So you remember I talked about stationarity, right? So arch and gauge model. So similarly, your volatility is a function of t. In fact, I made it explicit that it's a function of time, depend on past variables. So how can I say the whole xt is stationary, or at least weakly stationary? Is there a contradiction there? Remember, stationary time series xt, so is mean and variance have to be time independent. Well, sigma t is second order information and is explicitly time dependent. Is there a contradiction? So let you think for 5 seconds, okay? So is anyone want to talk about that or any idea? Is there a contradiction? Stationarity and similarly sigma t is time dependent. Well, it basically highlights the concept of stationarity. Okay. When we talk about stationary time series, we assume that the time series has run for a long horizon. Well, basically infinity. Okay. So on this long horizon, locally your sigma t can be time dependent, as shown in this kind of arch and gauge model. But overall, well, the spikes and non-spikes, well, they overall has a pattern. And overall they are finite, okay? So when we talk about stationarity, is talking about over a long horizon, overall is it looking like time independent. So sometimes it spikes, sometimes there's no spike. So these spikes overall have a finite magnitude. Something like that, okay? So it really doesn't contradict the notion of stationarity when you locally, your sigma t can be a function of t, okay? So sigma t, well, is just at time t, okay? So it's basically like your time series xt, ARMA model, AR model. So at time t, well, they can fluctuate a lot, but overall, is the mean deviate from 0 that much? Or is the variance, is the fluctuation deviate from a certain magnitude that much? Same in here, basically, okay? It's just that, well, the fluctuation are kind of clustered, but still, overall on a long horizon, it can look like stationary, okay? But when there's a time, when there's a financial crisis period in 2008, 2020, well, it kind of close to breaking down that stationarity. Looking through A1 plus B1, really close to 1, okay? So if it's a financial statistics class, I'll at this point introduce a non-stationary gauge, but this is not, okay? So I'll jump to another important topic, okay? Which is the end of chapter 3, actually. It's about forecasting, okay? But if you're interested in this topic, so yeah, let me know, okay? I can talk to you more about that. But for now, let's go to look at another topic, which is chapter 3. So let me go to the lecture note first. So this is the end of chapter 3 about forecasting and prediction equations, okay? So I hope I can go through that quickly. So we've talked about modeling for a long time. Hey, how about forecasting? So if we want to do forecasting, we need to have a measure of what is good and what is bad forecast, okay? That's the first thing. And we introduce the mean square prediction error. This is the most traditional kind of error. So if you don't have a specific application, so people usually use the squared error. But if you have a specific application in mind, perhaps some other form of error is more appropriate. But here, let's stick to the mean square prediction error, which is defined as the MSPE equals to the expected value of your L step ahead forecast, in fact L step ahead random variable, minus your L step ahead forecast, which is denoted by xt bracket L, where your xt is stationary. And your xt plus L is the L step ahead random variable you want to forecast. And we assume that the current time is t. So if the current time is t, it means something. It means we observed, so we've observed information up to time t. Or we say we have ft, right? A curly ft means information up to time t. And as last lecture said, so if you want to be more formal, it's a sigma algebra generated by your time series xt. Okay, so what is xt bracket L then? Xt bracket L is the L step ahead forecast. So whatever you put in, okay, given your information up to time t. So of course, by definition, xt bracket L is something contained in the information up to time t. But that's the setup, so we have a measure of what a good estimator for xt plus L is for an L step ahead forecast. But is there a best forecast that we can calculate? Well, with respect to the mean square prediction error, and that is, there is indeed a best forecast. And it boils down to decomposing the MSP in this way. So using law of iterated expectation, it equals to by the law of iterated expectation. What's my notation? E sub t here. The expectation sub t is expectation conditioning on information up to time t. Okay. So therefore, this is indeed the law of iterated expectation. Law of iterated expectation, the most general is, let me remind you, so reminder. So there are two sets of information, two sets of sigma algebras. So A is actually a subset of B, curly B. Information set A is actually a subset of B. Then the most generalized form of law of iterated expectation is, well, you're conditioning on the more information on B, and then condition again on the coarser information A, which is a subset of B, will be just the same as conditioning on the coarser information A. That's the law of iterated expectation, okay? The most generalized form. So here, I'm using the law of iterated expectation, where your B is the information up to time t, the ft, right? But what is A? Well, A is the empty set. Whenever we take marginal expectation without any condition, meaning we're conditioning on nothing. Conditioning on nothing is conditioning on the empty set. So here, the law of iterated expectation we use is B is the ft here, A is the empty set. So why do we write it like this? Well, the MSPE is that the outer expectation and the inner expectation. Let's expand this first. This is xt plus L squared minus 2xt plus L, and then xt bracket L, and plus xt bracket L all squared. And this is what? Well, this is expectation E sub t of xt plus L squared minus 2 times xt bracket L e sub t of xt plus L minus a plus xt bracket L all squared. Okay, how can we simplify like this? Well, xt bracket L is contained in the information up to time t. So expectation sub t, well, relative to information up to time t, xt bracket L is a constant. So we can take it out like a constant. Same here, xt bracket L all squared is a constant relative to this e sub t. Well, and then what to do with this? Well, we differentiate. With respect to our xt bracket L, you want to find the minimizer, right? So differentiation. So d of dxt bracket L of this MSPE. So if you do more, if you do measure theory and integration theory, you ask, can I exchange the integration and differentiation here? Okay, yeah, let's assume we can exchange that, okay? If you don't even know what I'm talking about, let's forget that. So differentiation, yeah, take it inside the expectation sign. Well, differentiating this is a constant, okay? With respect to xt bracket L, that's 0 minus 2 times, well, this is linear with xt bracket L, so it's just what's left is e sub t of xt plus L, and then plus this 2 times xt bracket L. And if we set this derivative to 0, so this will always be 0 if and only if your xt bracket L is e sub t of xt plus L. So this will be the best L step ahead predictor and when we say best or worst, it's always with respect to a certain measure. The measure is MSPE. Okay. So that is how we derive the best forecast. So as long as you have the ability to calculate these conditional expectation, then you will know the best L step ahead predictor. Okay. Now xt plus L can be a very complicated time series. Doesn't matter if you can calculate this conditional expectation up to with information up to time t, then you are fine. But most of the time, well, you cannot. Okay, so you can only approximate. Most of the time, these are either too complicated or is too time consuming. Okay, so if you want to calculate this kind of forecast thousands of times in every second, thousands of times may be very small nowadays, okay, maybe millions of times every second, then perhaps an approximation is to be called for. And when you want to do approximation, so the first simplest kind of approximation is, how about linear forecast, okay? So here, xt, this time series xt, we only assume is stationary here. But other than that, well, it can be anything. It doesn't need to be an ARMA model. It can be a very complicated non-linear time series where you don't have a clue how to calculate this conditional expectation up to time t. So let's simplify this. Now let's talk about linear forecast, shall we? Maybe that's easier to calculate, even for a very complicated time series. So the motivation is sometimes this is too difficult to calculate. So then we consider linear predictor. Now with linear predictor, okay. Linear in what? So we restrict the class of linear predictor to be linear in, of course, in the data that we have. So still use this as notation, xt bracket L, okay? So don't mix up with the best linear, the best L-step ahead predictor, which can be highly nonlinear, okay? So here, we explicitly restrict this to be a linear forecaster given your data x1 up to xt. So your current time is t, you observe x1 up to xt. So to minimize, the MSPE, so what is the MSPE? The MSPE now is, with respect to this class of linear predictor, the expectation of xt plus L minus alpha naught minus the sum of alpha j xj, j from 1 to t, all squared. Well, again, you can do something about estimating this alpha naught and alpha j theoretically. So if you differentiate with respect to, let's do alpha naught first and set its derivative to 0. Then basically, this is what you get. Okay, so let me do this quicker. This is 2 times xt plus L minus alpha naught minus the sum. So you should be able to do this very quickly. So it's 2 dropped, and then write the thing inside, and then differentiate the thing inside with respect to alpha naught, which is minus 1, right? And this whole thing is 0, okay? So that is your expectation of xt plus L minus xtl times x naught equals to 0, where your x naught is 1. So let's assume your x naught is 1. If we do the same thing for alpha j, so now you differentiate with respect to alpha j and then set the derivative to 0. So you get this, okay, so it's very similar, 2 times xt plus L minus xt bracket L, and then times minus xj. That's 0, okay? So it implies that the expectation of xt plus L minus xt bracket L times xj, that's 0, okay? So that basically is your prediction equation. So let me summarize that. So your prediction equation is about linear forecast, first of all. And it's this, expectation of xt plus L minus xt bracket L times xj is 0, where your j runs from 0, 1 up to time t. Okay? So you can actually calculate the value of this alpha. So if you write all this equation down, so this, and then minus, alpha naught xj minus alpha 1 x1 xj minus alpha t xj. That's 0 for j from 0, 1 up to time t. So if S H is the ACVS, then you can write this whole set of equation in terms of the ACVS. So as t plus L minus j, and then minus alpha naught. Well, this is different, minus alpha naught expectation of xj, so this should be mu, and then minus alpha 1 as j minus 1, that should be minus, sorry, so minus all the way up to alpha t expectation of xt xj, this is as j minus t, or t minus j. And this whole set of equation is true from one to t actually. Okay, so when we say xj is x naught, then x naught is actually 1, okay? It's actually not a random variable, so you cannot involve that with the ACVS. Okay? So from this set of equation, can you solve for alpha naught, alpha 1 up to alpha t? Well, you can. Okay? Solve it in terms of, so this is something I give you as an exercise. It's actually written in the lecture note. Okay, solve in terms of the ACVS for alpha naught, alpha 1 up to alpha t. And then estimate. So this is then standard. So estimate by substituting said j equals to your data. So your data is 1 over t sum of what? Just x s plus j minus x bar xs minus x bar, your s from 1 to t minus j, right? Something like that. Your t is the sample size, right? x1 up to xt, that's what you observed. So it's basically a set of equations involving the inverse, again, in a matrix with all the ACVS inside. You substitute all these ACVS with this estimator, okay? So many estimators you have learned is like that. The Walker estimator is a one prime example, okay? So here, linear forecast with prediction equation is similar, okay? But what if we're dealing with linear model already as a special case? Then we don't need to do this linear forecast approximation, right? For linear models, certainly the forecast should be linear, isn't it? Well, you will be correct, actually. So forecasting for stationary ARMA model it will be having something let me show you the forecast first, the best forecast, which is also linear. So it's stationary, so suppose xt can be written as this MA infinity form. It's stationary, so it can be written as an MA infinity. And let's suppose your epsilon t is IID. So sometimes I write IID like this, okay? If it's not IID normal, then that means it's just IID random variable with mean zero and variance sigma squared. Okay? So I don't know its distribution. So your XTL is E sub t of xt plus L. That's the best forecast. So I'm not doing any approximation here. I just go with best forecast. And that will be E sub t of this whole sum, right? It's from j from 0 to infinity. Your psi j epsilon t minus j. That's the MA infinity form. Now this MA infinity form can actually be calculated as, decomposed as two parts. So one part is j from 0 to L minus 1, psi j epsilon t plus, t plus L. What have I done? So t plus L minus j, sorry. Your time t is t plus L, okay? So it's t plus L here. So it's t plus L minus j plus j from L to infinity. The same thing, psi j epsilon t plus L minus j. So why do I decompose it like this? Well, because you can see immediately this part is not contained in FT. You substitute j from 0. Now j is 0, this is epsilon t plus L. When j is 1, epsilon t plus L minus 1. Still ahead of time t. up to when j is L minus 1, epsilon t plus L minus 1, that is epsilon t plus 1. This is still one step ahead of the information up to time t. So they are all in future. So the whole thing is not contained in ft. Relative to this, when j equals to L, this is epsilon t. When j is L plus 1, epsilon t minus 1, and so on and so forth. This is all in the past, so it's contained in ft. So you know that already. So when you calculate, when you do conditional expectation like this, for something not containing ft, well, this basically becomes marginal expectation. Marginal expectation of this, of course, is 0. And conditional expectation up to time t, for something contained in ft, this becomes a constant. So the value of this expectation is just this, okay? And we can write this summation back from 0 to infinity. This is psi k plus L epsilon t minus k. So compare your xt to this xt bracket L. Well, they're almost exactly the same, except your xt is psi j, your xt bracket L is psi j plus L, basically. Okay? So otherwise, everything is very similar. Okay? So with this, if you know the exact MA infinity representation, say from your real data, you fit the model, so you fit an ARMA model, so you know the MA representation approximately, then you can do forecasts like this. So xt bracket L will be, okay, I shift the estimated psi coefficients here, multiply with this epsilon t minus k, okay? And this form actually is convenient. Now, let's look at this form. In looking at something called the L-step prediction variance, so you got your predictor, so what is this variance? So first of all, with respect to the best forecast, your L-step prediction variance well, it's actually given by sigma t, sigma square L. So L, of course, represents the number of steps we're talking about in our forecast. So that's xt plus L minus the best forecast, E sub t of xt plus L squared, okay? So that's basically the MSPE when xt bracket L is indeed the best forecast, okay? So for ARMA model, so for this ARMA model, your xt bracket L, well, we just proved that this is psi k plus L epsilon t minus k, right? Then what is your L-step prediction variance? So your L-step prediction variance is this xt plus L, which is sum of j from 0 to infinity psi j epsilon t plus L minus j. And then minus xt bracket L, which is from L to infinity psi j epsilon t plus L minus j, right? So we just proved that. So these two are the same, okay? I write it because now I can immediately see that this is just expectation of sum of j from 0 to L minus 1 psi j epsilon t plus L minus j squared. Right? And so their RID, so expectation of this sum of squares is sum of the squared expectation, right? For this IID random variable. So there's sum of psi j squared, j from 0 to L minus 1, expectation of this epsilon square, which is just sigma square. Okay? So you should at least be able to derive this L-step prediction variance, okay? And look at the prediction, so to assess if this is good or not, okay? So very quick example. Before I finish the lecture. So your xt, let's say is a, let me see how much time I have. Okay. Very quickly, so this is armor 1, let's say, so it's phi xt minus 1 plus theta epsilon t minus 1 plus epsilon t, right? So that's your armor 1. Again, that's your epsilon t by IID, mean 0 variance sigma square. So very quickly, your xt will then be equals to 1 minus phi b inverse, right? Applied on epsilon t plus theta epsilon t minus 1, which is sum of phi to the j epsilon t minus j plus theta epsilon t minus j minus 1, and this is j from 0 to infinity, right? This armor 1 model. This calculation should also be in the lecture note. If it's not, then yeah, take it from here. So this equals to, well, you need to, certainly you can see that many epsilon t minus j minus 1, they just shifted one time length ahead. So if you collect like terms, the very first term is epsilon t. And starting from the second term onward, so this when j equals 1 on the left hand side, this is collected with j equals 0 on the right hand side. Okay, when j is 2 on the left hand side, this is collected with j equals 1 on the right hand side. Okay. So this should be what? J from 1 to infinity. If we fix it as epsilon t minus j, then this is theta j plus theta j minus 1 times theta, right? It's phi j times theta. Okay, and it was when j is j minus 1, then this is replaced by j minus 1, then this becomes epsilon t minus j. So that's exactly the case. epsilon t minus j. So if you're a little bit confused, so think about that, okay? So I'm collecting terms on both sides, only as epsilon t minus j, okay? Epsilon t minus 1 here is when j equals 1, and epsilon t minus 1 also appears in here when j equals 0, and so on and so forth, okay? So I collect all those epsilon t minus j and sum those corresponding coefficients. So this equals to epsilon t plus phi plus theta, phi to the j minus 1, epsilon t minus j, yeah? So just 1 more minute, please. I should have started. So therefore, your psi 0 is 1, and your psi k is phi plus theta, phi to the k minus 1 for k larger than 1, right? And so if you calculate any prediction variance, so therefore, any L-step prediction variance for the best forecast for this ARMA 1-1 model will be sigma squared times sum of this psi j squared, j from 0 to L minus 1, so this is, when j is 0, that is 1, so sigma squared, 1 plus sum of j from 1 to L minus 1, psi j squared, psi j is phi plus theta all square, phi to the j minus 1 all square, so 2j minus 2. So you can simplify this and get the L-step prediction variance. This way, okay? So for this ARMA 1-1 model, I've shown you this calculation. All right, so in exercise you'll do more. So I will see you guys next week. So next week we will start multivariate time series, okay? So for the last 4 lectures, we'll be on more general multivariate time series. All right, see you guys next week.
Because if they all come over,